Avogadro's number is central to what we think of as chemistry because it connects our measurable quantities of mass to those tiny little particles of atoms that we can't see. But just converting from atoms to moles and moles to grams doesn't tell us everything we need to know about the atom. Dalton's atomic theory was the first complete theory based upon evidence, but he didn't know, and at that time, nobody knew about the pieces of the atoms that contributed to their mass and made them different from one another. So within an atom, we know that we have a proton, which is what determines the atomic number and the identity of the element. In that atom, the positive proton is balanced electrically by the negative electrons, but the electrons are very small in terms of mass and in terms of size. The thing that wasn't discovered until quite a bit later from the others was the neutron. But before the neutron itself was discovered, there was a knowledge of mass of atoms being different from the atomic number, and enough evidence to prove that not all atoms of the same element are identical, or that we can have different versions or isotopes. When we have different isotopes of an element, it's still the same number of protons, but the neutrons vary, causing them to have different mass numbers. One way we show that is with this symbolic notation here, using the symbol, the atomic number to tell the number of protons, and the mass number to tell the total mass of that isotope of the element. In that case, the number of neutrons is what gives the added mass beyond the protons to give us our mass. So some elements have only one naturally occurring or stable isotope, but some isotopes have many of them. And when we have more than one, those extra or those different isotopes all contribute to how we look at that element in nature. The naturally occurring percentage of each, space there for a minute, is called the natural abundance. And when we want to know about that, we have to analyze a sample to find out. The most common way to do that is mass spectrometry. A mass spectrometer, which looks kind of like this in its simplest function, takes a sample of an element or compound, heats it up to make it a gas, ionizes it by knocking electrons off, accelerates those ions by using the charge, and then when passed through a magnetic or electric field, the different mass isotopes are affected differently by that same charge. So they all have the same ionic charge on them, but the heavier ones are not able to have their path changed as easily. We don't need to know all the mechanics of it, although we will talk about that some. The idea is that the mass spectrometer makes a mass spectrum. It takes the one element or one sample and breaks it down into the abundance of each different isotope. This is super common and super helpful in understanding organic chemistry. Organic chemistry you'll take in college if you continue down a chemistry, biology, or medical path, and focuses on the chemistry of carbon. When we look at that, there's lots of intricacies to our graphs. But whether it's a really complex graph based upon a really complex compound or a very simple graph from just an element, two things remain the same. The x-axis focuses on which isotopes or which masses exist within that element or compound. And then the y-axis is the intensity, or tells us the abundance of those isotopes. We'll focus on simple elements and compounds in AP Chem. So right here, for example, this is zirconium. Zirconium has an average atomic mass that is around 91.2 because we have isotopes with masses of 90, 91, 92, 94, and 96. We've got a spread of those, and only by vaporizing our sample, ionizing our sample, and then sending it through the mass spectrometer can we separate those, because they all have the same number of protons, They all have the same number of electrons, and they all have the same chemical properties. They only differ in their atomic mass and their nuclear properties. So as it zips through here, the lightest isotope, the zirconium-90, is most impacted by that magnetic field. Its light mass makes it very easy to kind of get it to veer off course or to change its path. It has the least mass, least inertia, or maybe least momentum. The heaviest isotope has the most inertia and wants to stay closest to in a straight line. So that zirconium-96, although it is impacted by our magnetic field, it's not as much. We can think of it as like a motorcycle taking a turn, which can take it very tight because it's nice and light and maneuverable, as opposed to like a semi, which takes the turn slower and wider because of that added mass. After we have split it into that, we need to be able to understand it. Right here is a relatively simple graph that's a mass spectrum of boron. It tells us on the x-axis we have boron 10 and boron 11. On the y-axis, it gives us our abundance. It's not giving it as a percentage here, but just as relative amounts. This one is 4 times taller than that. It's a 4-to-1 ratio of boron 11 to boron 10. So that tells us a couple things that allows us to know that it is boron and about this sample of boron. First of all, although we did initially say it was boron, we can prove that it's boron by thinking about the masses of those. The masses are in the 10 to 11 range. AMU, remember that's the mass of an atom, which we can also connect with Avogadro's number to molar mass, but that's on the periodic table. And boron's the only thing that has a mass between 10 and 11. Beryllium is 9, carbon's 12, so that 10 to 11 range has to be made of atoms of boron. The relative abundance here shows that the peak with the mass of 11 is way taller than the peak with the mass of 10. That means we have way more boron 11 than we do boron 10. Its abundance is greater. That would allow us to kind of estimate or connect to our average atomic mass. The peak 11 is much taller than the peak 10, like we just said, which means that the average of these two has to be a weighted average, accounting for the fact that out of every 5 atoms of boron, 4 of them are going to have a mass of 11. So the mass would be much closer to 11 than to 10, which connects to the value that we see on the periodic table. So mass spectrometry connects to mass number, isotopes, and the natural abundance in a way that lets us take data and graphs to prove what we know about the different isotopes, neutrons, and abundance of the samples of elements, atoms, and molecules in a compound.